So now that you've already seen what happens to images as objects are placed in different places for a convex lens or for a concave lens, let's try to do this with pure math. And let's try to connect what we connected just like in the mirror formula, the image distance, the object distance, and the focal length. Now, one little refresh about the sign convention. What was it? Anything up is positive, anything right is positive, anything left is negative, anything down is negative. And the mirror or the lens is always placed at the origin. The pole of the mirror or lens is always placed at the origin, and all distances are measured from the pole, which makes it so that a concave mirror has a negative focal length, a convex mirror has a positive focal length, and a convex lens has a positive focal length, and a concave lens has a negative focal length. And you can see all of that, why it's true, it's pretty trivial. With this all background set, let's take our first case, a very simple one, and try to understand or derive what's called this lens formula. Of course, the derivation is easier than just remembering it. No, we won't want you to remember it blindly. So we'll give you the derivation. So let's see what happens. Let's take our principal axis, let's put our convex lens there, let's take an object that is, let's say beyond 2f, right? Just as a case. And we know where the image is going to form, between f and 2f. Take one ray, push it there, take the other ray through the pole, it goes unaffected. So the ray parallel goes through focus, the ray through pole goes unaffected. Great. So now what do you have with you? A chance to play. And what do you want to connect? U, let's call it the object distance, V, the image distance, and F, the focal length. So let's move this to be able to understand this a little better. Let's put it out there and let's begin to understand what we need. So we're going to again look for a pair of similar triangles or two pairs of similar triangles. So as you can see there, does one of them strike out at you? That's right, yeah. The two similar triangles over there, the small ones on the right side of the lens. And what do you see there? Right? That's right. You write them out. What do you get? H by H dash, or the image size by the object size. Oh, I'm sorry. If it's H by H dash, it's the object size by the image size. And you write it down there. And what do you get? That's equal to that length by this length. And what is that length? It's just F. And the other length is, that's right, V minus F. Because the overall length is V and the smaller length is F. So we have one equation. So you take those two similar triangles out and write that equation, and that's what you get. Now what do we have to do? Look for another pair of similar triangles, right? And there you get one more. And just by our old analogy, how are these two triangles similar, by the way? I assume that you know how the other triangles are similar as well. How are they similar? Because the opposite angles are equal and one of the angles are 90 degrees. So two angles for two triangles are equal. What does it mean? AA similarity, right? And that means that the angles will be equal, the sides will be proportional. And using that, we write our first equation. Now let's do that for the second equation as well, right? What do you get here? The same H by H dash, yeah? And that's equal to what in this case? The sides are proportional. So it has to be equal to that side by this side. And what do you get now? What is that length? The entire length is U and this entire length is V. So it's going to be just U by V. Now what do you have here? H by H dash is common. So equate those two, right? Then cross multiply. You get a very similar looking, very familiar looking equation. Divide the whole thing by UVF. Don't ask me why we do that. Why do we do that? That's right. It's an argument of beauty. So you get something, right? Something involving 1 by V, 1 by U, and 1 by F. But what do we know now? One of those quantities is not positive. And what is that? The focal length, is that positive or negative? That's right, it is positive. What about V? Clearly it's on the right side, so it is positive. What about U though? U's on the left side, right? So therefore it is negative. So if you replace that over there, what happens to it? What was 1 by V plus 1 by U equals 1 by F, what does it become now? U becomes negative, so replace U with minus U, and what do you get? 1 by V minus 1 by U equals 1 by F. And that's the formula for lenses, or the lens formula. 1 by V minus 1 by U equals 1 by F. Now, have we taken every single little case of a convex and a concave lens and proved it to you? We don't, and we don't intend to do it as well, because it's very easy to see from what we've shown you here. Because all the rays in the other cases also follow the same rules. Therefore, we must be able to find a very similar set of similar triangles. Great. So we now have one more toolkit in our bag, which is 1 by V minus 1 by U equals 1 by F. It connects image distance, object distance, and the focal length. So we've done a lot about lenses, a lot about mirrors. We've derived the mirror formula and the lens formula. We've come a long way from where we began with a little plane mirror. Plane mirrors form virtual images. They are as far away behind as this. From there, we've come a long, long way. Now we know how to deal with concave mirrors, convex lenses, concave lenses, right? And we can derive where, if you know where the object is, you can find out where the image is. But let's say you want something very, very practical. You want to create a convex lens. For what purpose? For the purpose of magnification. So how large must you create it? Lots of questions are there, right? So you need to know what this quantity called magnification is. And what is this magnification? What do we know by magnification? Some object is this big. I want to make it appear that big, right? So if I want to do that, and then what am I achieving? Some kind of a magnification, right? So how do I quantify this? So this by that, won't that give me a good idea about magnification? So that's what we'll do. So what is this? H, or the object size. And what is that? H dash, or the image size. These two seem very familiar, right? Because both in our derivations of mirror formula and lens formula, we kept playing with this quantity, H dash by H, or H by H dash. So what do we do now? We define that as magnification. So it's not a new quantity, but it's a new name to a quantity you already know. Magnification. So what do we know now? Whenever H dash by H is greater than 1, what do we know? We've achieved a magnification in the true sense. We're actually going to see the object being bigger than what it actually is. And if it's less than 1, we see it being smaller than what it actually is. So if you have to design a mirror, if you're going to design a magnifying lens, you need to design it in such a way that at a reasonable length, it'll give me some magnification, right? Because if I make the focal length so small, I have to keep it so close to be able to see it magnified, it kind of loses its point. So it's going to help us. The understanding of magnification is going to help us in designing a lot of physical devices like the telescope, the microscope, which you will learn about a little later. So the idea of magnification is a lot more interesting than it might immediately seem. It's a little more complicated than just understanding, okay, this is magnification. Let's see what it is. Right? What is magnification? H dash by H. Can we go one step more than that and start connecting image and object distance to it? How do we do that? Let's try and understand what really happens. So in the case of lenses, like we saw, there are a set of similar triangles that are in such a way that H dash by H is directly equal to V by U. Now the first question is, if H dash is negative, what would that mean? The image is inverted, right? Because that's when you measure the distance from the principal axis, it would go down. And we know by our convention, down is negative. So once you know that, what do we want now? We're a little greedy. We want the magnification's value to also give us information about whether the object is erect or inverted. So if the magnification is greater than 1, the size of the image is larger. If the magnification is positive, then the image is erect. If the magnification is negative, then the image is inverted. So we're trying to get as much information as possible from that little quantity called magnification. So in the case of lenses, what do we see? If we keep it H dash by H as V by U, therefore the magnification will be just V by U, because like you can see, in all the cases, wherever V by U you calculate, let's take a normal case like that. What happens when you calculate V by U? V is positive but U is negative, so you get the value as negative. Great, which is what you want because the image is inverted. Now let's try and do this. So what is the magnification for lens? It is V by U. Now let us do this for a mirror. Right, let's take a concave mirror. Let's draw our object and let's just draw our image. And what do we see now? Let's take a very sneaky little ray and draw this such that it hits the mirror at its pole and comes back. Therefore, we have a new set of similar triangles where H dash by H also becomes equal to V by U again by similar triangles. But what about this case? If you take the magnification for mirrors also to be V by U, then what do you get? You get a positive value because V is negative and U is also negative. But is that what we see? We see that the image is inverted, right? So what do we want? We want a negative answer so that it accounts for the fact that the image is inverted. So what do? For mirrors, we take the magnification to be minus V by U. Why are we doing all this? We're doing this so that our convention of whether we take positive or negative also gives us information about whether the image is erect or inverted. So for a lens, the magnification is defined as H dash by H, which turns out to be V by U. For a mirror also, it's defined as H dash by H, but to account for our convention, it becomes minus V by U. So so if you really understand what we are trying to do, we don't really have to remember it's V by U for lens minus V, none of that, right? Magnification is positive when the image is erect, magnification is negative when the image is inverted. And that's all you have to know.